And general seekers of truth, welcome to the video on L'Hopital's rule. I know this looks like it says La Hospitals, but it's pronounced L'Hopital, okay, after a great French mathematician. So now we reach this point from the previous videos where we try to calculate limits and we are unable to get past the indeterminate form. Even if you try some special trick of factoring, it's still kind of complicated to figure these out, if at all possible. So we use L'Hopital's rule, which is really a theorem, and it says that if x and y, if f and g are differentiable on an open interval, then and the limit of f over g takes an indeterminate form, then the limit of those two functions, of that quotient, is equal to the limit of the quotient of their derivatives. So what that means is we can re-attack the previous problems here, and since the original problems take indeterminate forms, what we can do is just take derivatives of the numerator and the derivatives of the denominator until we get somewhere useful. So let's revisit number 6. The limit as x approaches 2 of x cubed minus 8 divided by x to the 4th plus 2x minus 20. From above, we've already shown that they take an indeterminate form, so we can start now just by taking some derivatives. Derivative of the top is 3x squared. The derivative of the denominator is 4x cubed plus 2. Okay. Now we can actually try direct substitution. In the numerator, we end up with 3 times 2 squared. In the denominator, we get 4 times 2 to the 3rd plus 2. So the top, that's 4 times 3, so that's 12. In the denominator, that's 4 times 8, so that's 32 plus 2, so that's 34. So this limit actually approaches 6 over 17. Okay, so that's us applying L'Hopital's rule. We started out with a limit that had indeterminate form, so we take the derivative of the numerator and denominator and try direct substitution again, and in this case we get a pretty nice simple answer. Okay? I also want to point out that you cannot use the idea of pulling out leading terms here, because the limit is not going towards infinity, the limit is going towards 2. Okay, so it's a little bit different than the other ones that we've seen. So there are some nice and useful ways that you could probably factor the denominator here, but that's not an easy task. Okay? You can also try some some types of synthetic division, but that's also not very straightforward. L'Hopital's rule gets the job done quite well. Let's take a look at number 7. We want the limit as x approaches 0 of e to the x minus 1 over cosine x minus 1. And we know that it already took the indeterminate form. Okay? So we can just keep on taking the derivative. The derivative of the top is e to the x minus 1. The derivative of the bottom is negative sine of x minus 1. And we're still looking for the limit. I've made a grave error. The derivative here of the denominator is not negative sine of x minus 1, because this minus 1 goes away. It should just be negative sine of x. So this is negative sine of 0, which is 0. Thought something seemed fishy. So this is indeterminate yet again. Okay. So far it seems like we've gotten nowhere with L'Hopital's rule. It seemed like we had something there, but that was just a mistake on my part. So now what are we to do? Well, use L'Hopital's rule again. So take this derivative yet one more time. So this becomes the limit as x approaches 0, and let's take this derivative, e to the x minus 1, In the numerator, so that's just e to the x. In the denominator, the derivative of negative sine is negative cosine of x. Okay? And now we can try direct substitution. E to the 0 in the numerator and negative cosine of 0 in the denominator. So in the numerator we get 1, in the denominator we get negative 1, so this turns out to equal negative 1. Okay? That's the correct answer. Okay? So the moral here is if you take this derivative, if you apply L'Hopital's rule once and it doesn't quite work, well, take the derivative again. Apply L'Hopital's rule a second time, because you can just treat this as your new f over g and take the derivative of that. Okay. So that leads us to our last example. What is the limit here as x approaches infinity of x over 5 over e to the x? So let's apply L'Hopital's rule. The limit as x approaches infinity of 5x to the 4th over e to the x. Okay. Well, if you plug in infinity to both the top and the bottom, you still get a large number over a large number. So that's indeterminate. So take the derivative again. Becomes 20x to the 3rd over e to the x. And that again is infinity over infinity. And you can kind of see where we're going with this. So take the derivative again, 60x squared over e to the x, and we get infinity over infinity. So that's also indeterminate. So take the derivative yet again, 120x over e to the x, and we still get infinity over infinity. Okay. So yet, still indeterminate. And let's take the derivative one more time. The limit as x approaches infinity of 120 over e to the x. And now we get 120 over infinity. So again, this is not correct arithmetic, but it's good for us to help understand a little bit that you have a constant, a term that's always the same, over a very, very large number. So this limit is going to approach 0 in the long run, because you have a finite number divided by a very, very large growing number. So it's going to approach 0. And maybe you can extrapolate and conclude, that exponential functions, e to the x, are just in the long run bigger than every single polynomial. Every single polynomial that you can think of is going to be smaller than exponential functions in the long run. Alright, so I will end this video here. We still have a few examples left, but we can maybe work through those in class. As always, if you have troubles, ask your teacher. Thank you for watching, and have a wonderful day.